Good morning, good afternoon, and good evening. I'm your host, Caitlin Stulick. I'm here with our presenter, Ted Huang, and our co-presenter, Angela Criswell. Thank you all for attending Rigaku's webinar series, X-ray Computed Tomography for Materials in Life Science. In this episode, Multiscale Structural Analysis with X-ray CT, we will cover how different CT approaches can work together to improve the way materials are evaluated, verified, and refined. But before we start, a few housekeeping items. This is going to be an interactive session, and I will be posting relevant links in the chat window. We'll be taking your questions live during the webcast and answering them during the session, so please do not wait until the end to ask. Please submit those questions via the Q&A button at the bottom of your screen, as we will not be monitoring the raise hand function. We will try to answer as many questions as we can during the webinar, and we'll respond to any unanswered questions directly after the session is complete. If for whatever reason you have difficulty viewing the webinar live, please note that it is being recorded and you will be able to view the recording beginning tomorrow. Okay, and with that said, I will turn it over to Ted and Angela.
All right, thank you, Caitlin, and thank you everyone for joining us for today's webinar, Seeing the Full Picture, Multiscale Structure Analysis with X-ray CT. So for the topic about X-ray CT, I've always wanted to talk about multiscale structure analysis. But before that, what exactly do I mean by multiscale? So imagine today you are, you just off from work, you just returned home, and now you're just relaxing, reading a book, trying to wind down, and suddenly the light just went out. But luckily, in this case, you know exactly what happened. You know that, oh, okay, it's the light bulb just went out. So what do you need to do? You only need to change the light bulb. Problem solved. And you're back to your reading. But this is just a single chain of issue, cause, and solution troubleshooting. So this is a single scale problem that you just encountered. So you only need one troubleshooting step. Okay, is the light bulb broken or not? And then one technique. You need to know how to change the light bulb. And then you're on your way. But a lot of times, this is not how trouble happens. So imagine today again, the light went out, but it can still be the light bulb, but you're not sure. It can be the light bulb, or it actually can be the breakers. Maybe the breaker was down. Or it can be because of the power line tower. Or it can actually be the whole city is out of power. You don't know. Right? So now you have to face multiple ways to verify what's the problem. If it's a light bulb, you change the light bulb. If it's a breaker, you change the fuse. And if it's a power line tower, well, probably you have to call the electricity company. And if it's a whole city is out of power, see if you have a backup power generator or not, then you probably have to just wait. So you're dealing with multi-scale problem. There are multiple scales, multiple troubleshooting steps that you have to go through. And then it requires multiple techniques to solve depending on what the problem is. So this is not just for this example in life. It also happens a lot, most of the time in your research or your manufacturing process. So for today's episode, you will learn what multiscale structure analysis is, what it is, and why it is important to your research and to your manufacturing, and how can CT help. So after knowing how CT can help, if you're interested in what kind of city system you would need to do the kind of multiscale structure analysis you want to do, we'll talk about that based on the limitations and requirements of different type of techniques. And then some of the practical strategies for general CT usage, or depending on you're scanning smaller or larger different scale samples. And lastly, we'll go through some examples of these kind of multi-scale CT studies. Now, multi-scale structure analysis, why is it important? We just talked about the example of reading a book and the light goes out. So let's talk about it in a way that's more akin to a manufacturing problem or a research problem. So here you can see this is a product. This is a respirator. Depending on where you are or who you are in the company, a lot of times maybe you'll have more streamlined process to tell you where the problem is. But depending on what type of problem you're facing, a lot of times you might just face this sample showing up on your desk with a note just simply saying, hey, it is not working. Well, why is it not working? How is it not working? You have to try to debug, try to troubleshoot. So we start asking questions. There are a couple possibilities I can come up with. Well, maybe it's a valve. Maybe the valve is not aligned. There's something wrong with it. Or it can be the filter can. Maybe the filter can is default. It's faulty. The filters are having something wrong with it. Or it can be further upstream. Maybe the filter particles inside the filter can is having something wrong. Now let's go through them one by one to see if you want to examine them, what you're dealing with. But before that, notice all these things you're actually already dealing with different scale in terms of the size. Like the valve, you're looking at probably millimeter scale defect. For the filter layers, maybe hundreds of micron. For the filter particles, it can even smaller, maybe even sub 10 micron or so. So let's look at the valve. Let's say, okay, is the valve not aligned or alignment problem? Let's see what we can do and what are the possibilities. So misalignment or it can be a physical puncture that's causing it not aligning properly. Or it can be manufacturing error of the whole geometry of your valves. So for misalignment, chances are I'll just look at it with my eyes, right, to see if someone didn't put it together correctly. For physical puncture, maybe it's not as straightforward, so maybe I need some help, maybe some leak tests or some other examinations. For manufacturing error, if it's very subtle but still effective, you probably need to do some nominal to actual comparison to figure out, okay, yeah, there's something wrong or some misalignment to my bulb. What about the question of the filter layers? Well, am I missing a layer in the filter can? Is there full inclusion in those particles inside filter cans? Or just simply these effective filter particles are not packed properly or uniformly? Now you also face something that you have to do, like, okay, you probably have to crack open the filter can just to look at it with maybe not just your eyes, but some tools assistance. For full inclusion, you probably already have to use some optical microscope to help you. And for uneven filter material packing, you're asking something that's more three-dimensional. So just looking at 2D might not be enough. You probably had to do some sectioning, so including more time and more sample. You're starting to see a pattern here. You're still just asking questions. You don't know exactly what's wrong yet, but you're delving deeper into multiple avenues and more in-depth process and expertise. So let's say for the particle defective question, you also face the same. Is it fractured? Am I missing some coatings on the particles, or the compound is just not right? Now you need to use more and more intricate techniques, high magnification optical microscope. Some SEM might even need to be involved, or there are some cases you had to consult other departments who made the particles. So the challenge we're facing in either research or in manufacturing is that to answer these questions, oftentimes there are just too many sample types you have to use. So you have to invest in a lot of high resource commitment, both in time or expertise. And other times, it's often destructive. A lot of times you have to crack it open, you have to destroy it. So now it brings more information that you have to consider before you can make conclusions. Like, okay, is there sampling bias? Did I cause the thing to break, or is it already broken when I crack it open? And then because it's destructive, you do one examination, maybe you have to do another one for another, and both are destructive. You have to make more samples. That loops back to the first point that, okay, you need more and more sample types. Now, for a established product line or research topic, this is where people streamline or optimize the process. Like, okay, most likely are some of the places that you have to look into. But things change. Maybe you're making a new product. Maybe you're trying a new manufacturing techniques. Maybe you have a new like a resource, like a source you get your components coming from. So you still have to face these kind of challenges that's not as optimized. You have to be adaptive. So wouldn't it be nice if there's a technique that is an analysis technique that can either downright just tell you, okay, what's wrong? You can just see it, or at least point you to the right direction before you dive deeper into either avenues to try to investigate. And to do that, this technique has to have a couple qualities because we already established this is a multi-scale issue. That technique has to have a wider scale range of observation. And also, it has to be non-destructive or at least minimally destructive when it absolutely requires. It's not like, okay, it can't be destructive technique is a default. So before I dive into these wonderful technique. I would like to have some of your input. So let's head towards our first polling question. I would like to hand over to Angela.
All right, guys. So this question is for you. I'm going to launch it now. And what we'd like to know is how challenging is multi-scale structure analysis to your application? Is it something that you face often? Or maybe it's not really a big issue, but you're interested in additional techniques? Or maybe it's just not an issue for you at all. So if you could pick one of those three options. Right now we have about 42% participation. So I'll wait just a few more seconds and Ted, and then we'll wrap it up. Okay.
Yeah.
So I'm going to end the poll in 3, 2, 1, and I'm going to share the results with you. So it's pretty split. 36% say it's an issue they often face. 57% say that's not a big issue, but I'm interested in additional techniques. And a lucky 7% say it's not an issue at all for them. So I'm going to stop sharing this and send it back to you, Ted.
Okay. Thank you, Angela. And also thank you everyone so much for answering that poll question. It really tells a lot about where you're coming from and what might be the challenge you're facing, and hopefully we'll be able to help you address that. So like kind of what I can also imagine, this is something that's very common. So you definitely already have some idea or have some established ways to kind of navigate this kind of challenge. And for the 7% that's very lucky, I hope this webinar will be still very helpful, but maybe in the future when this kind of problem arises, you will remember this kind of technique that will be very helpful for you. So obviously, it's kind of like not really a spoiler, but we kind of expect this technique I'm going to talk about is going to be X-ray CT, right? So how CT can help you with multi-scale structure analysis. Just to brush up some memories, or in case some people are not as familiar with CT. So what exactly is CT? Just very quickly, we do an overview. So this is an X-ray technique that simply you just scan your sample by exposing it to X-ray source. The other side, we have the detector to take up the signals after your sample absorbs the X-ray. We take a lot of the images by rotating your samples or your detector or source together to collect a bunch of 2D images. This is a process we call scanning, or CT scanning whenever I heard people talk about it. So with all these 2D projections and with the modern computational advancement, we can actually do it at just commercial level PC to do a reconstruction, basically put all these 2D projections back into a virtual 3D space. And then you end up with a 3D data of your sample. So essentially make a digital clone, put your sample into the digital world so you can do whatever you want, whatever you can, multiple times, slice it open, so on and so forth. And you can see this process, there's no destructive involved. The only place that might be destructive is when you're trying to put your sample in the chamber, right? So once you can put your sample in there, there's no destructions. Now, the second thing I mentioned that this technique needs to be helpful is also the scale it can cover. So it doesn't help if that CT can only scan one scale. As you can see here, CT is having a nice overlap with many techniques, including your eyes, and also optical microscope, and down to the level of electron microscope. So it's providing you with that wide range of scale that you can look at different factors. So let's get back to this example that I talked about, the respirator. So let's see what how CT can help. So in this case, the first thing I do with this sample and to ask these questions was I'll just put the whole thing inside CT to see what CT can tell us. So with the whole scan of the whole assembly, we can immediately, with X-ray vision, literally, to see through everything to decide, okay, am I already seeing something wrong? Or should I take a closer look at the filter can, or look at the valve attachment point to see if I can see anything just by this kind of magnification? And if I can, great, I have my problem solved, I can move on to the next step. If not, let's take a closer look. Specifically, the first question we ask, is the valve not aligned? So, okay, let's look at the valve area. So for the evolve area scan, we can highlight and specifically just look at it and then slice it open. So you can see on the right, this is two parts. On the top is the filter can area, and the bottom is a mask area. So you have these as if you cut it open using ON or SEM to see the attachment points and see if there's any sealing issues or the gaps you can already tell. And because CT is 3D, so you don't have to just rely on 2D information. You can also do the same thing in 3D. So here is, again, the rendering, and I slice it open in 3D to look at the connection joints. And then you can further ask questions and fine tune them to separate the top and two color. Basically, one side is the filter can. The other side is the valve on the mask. In this case, I demonstrate something like, okay, I can ask about the thickness distribution of the valve, if there's any deviation from my product, from my CAD drawings, then I can notice that. So you basically can do the actual comparison just virtually. Now, what about some other questions I was asking? What about the filter layer problem inside the filter can? So let's look at the filter can. So in this case, I scan the filter can and let me show you the crop area of the filter can inside, show us how the layers are on top of each other. So you can see there's basically only two type of main layer. One layer is a darker, lighter material. I think it's probably carbon particles. And the bottom are highly higher density particles. That's likely the active ingredients that's actually filtering whatever this filter can is designed to filter. So we can, again, do virtual cross-sectional views to see how they pack together throughout from top to bottom to anywhere in your filter, and then examine if there is any distribution anomaly. And you don't have to resort to just one slice. You can also average them out to stack them together to learn about the pass-through, because it may look very uniform, but when you stack everything together, you'll notice, oh, actually there are area that's having less density of certain particles, so that will create potential leakage or a weaker filtering channel that the whatever toxic gas that can pass through. And we don't have to just look at it in 2D again. We can look at everything in 3D. So in this case, let's look at it, and I kind of just, okay, let's separate the top layer, the lighter particles, highlighted here, segmentation in different colors. You can ask specific question you can. But in this case, I was more interested in the higher density particles at the bottom. So this is the intensity distribution, because I noticed among them, there's also some intensity differences based on how dense they are. So in this case, I individual highlighted them just so I can do more analysis in this case as a demonstration. Further on, we can also ask a question about the filter particles. In this case, I did at this step, I did break open the filter can just to look at the particles, because we're stepping into higher resolution here. And the reason why, I'll talk about it later when we talk about different scale of sample preparation. You can see here, I took a particle out, and you see the scale bar here. We're already looking at the scale bar as 50 micron, but we can look at smaller features like the porosities inside, like highlighted here in 2D, and you can also do that in 3D. So just look at the morphology of your particle and then slice it open in 3D just so that you know exactly what you're looking at. And you can ask the question, oh, is there a coating there? You can see there seems to be a higher density coating, and just a demonstration. I did a porosity analysis of these kind of particles inside this kind of sample that I just prepared. So now let's look back at what we achieved just by using CT. I didn't use SEM. I didn't use any other techniques. We did a full scan of the respirator and have the X-ray vision to just immediately get a top-down view of, okay, where do I want to look at? And what about the question we asked, is the valve not aligned? We did the examination of the valves. With the filter cans within the filter layer, we also look at the filter layer particle distribution. For individual particles, we were also able to do that with CT, and then all of them are all 3D data. So they're not like different data. One is an image, one is a peak, one is spectroscopy. You can still do those if you need to, but CT serves as a very good top-down, comprehensive, wide-scale coverage for you to start, or even just solve your problem altogether if you can already see something's wrong. So with this, after showcasing this, I feel like maybe there will be some questions. So let's head into our first Q&A session.
Yes, and please remember to drop any questions you have in the Q&A button. We have our first question here. How long were the scans for the respirator sample?
Okay, yeah, that's a good question, right? Because okay, it doesn't make sense if the scan is taking like your whole week just to have that image, right? So for these ones, there are a couple different scans. I did the whole respirator and the cans. They're actually quite fast in my opinion. They're only like 17-minute scans. For the particles, though, that the one that I break out of the filter can to do a high resolution visual examination, that one took a bit longer. That one was like 2.5 hours or so. So yeah.
Okay, thank you. And we'll do one more question. What was the energy that you used for these scans?
Yeah. Okay. Yeah, that's also a good question. So again, a couple different energies for different scale, but it's actually they are the same. A lot of them are the same equipment, but you can adjust the energy within the range of the source availability. So for the whole respirator, I scanned, I think it was 200 kilovolts. Yeah. And for the filter and the valve area, I think it was 130 kilovolts. The particle is a different system. It's using, we changed the target for that. So it was using a monochromatic X-ray. It was a copper source. So I think the energy for the X-ray for that was like 8 electron volts.
Okay. All right. Well, we will get to more questions throughout the webinar, but for now, we'll go ahead and close this out and get to those questions near the end. Please remember if you have any to just continue to add them throughout the presentation. All right, hand it back to you, Ted. Thank you.
Yeah. Yeah, thank you, Caitlin. And also thank you for the question. Those are really good questions. So let's move on to the next chapter. So after knowing how CT can help and also using an example of Earth separators to tell you, okay, what are the different scales you can look at, let's look at some of the limitations and requirements of CT so that you can have a better judgment. Okay, what kind of CT can help me, or is it even helpful at all? Because it's tremendously useful, but like any technique, it's not like, oh, this is the best thing in the world. It solves everything, right? There's going to be some balance you need to know, but they are still very helpful for your manufacturing process, I believe. So which CT system to choose, right? So what are the questions you need to ask, or what are the things that you did take note of? So first thing you need to know is there's a FOV, field of view, versus resolution balance that's happening for CT system. And I'll talk about what FOV is, and we'll talk more in depth just in a moment. But basically, you will have to know what your sample size is, or the sample size you're willing to go to, because it might involve some sample preparation or not, and the feature size, because it doesn't make sense if you're trying to look at something that's very tiny and you use a resolution that cannot even see it, right? You have to be able to see what you expect to see. So there's a balance between sample size and feature size I'll talk about more in depth. And then the next thing is sample composition, because it's an X-ray technique. So what's your sample made out of also matters. So is your sample made out of a higher or lower Z material, or is your sample denser or light or less density? Those will also play into the factor of choosing a CT system. So the first thing, FOV versus resolution. So just to reminder, or just to introduce, what is field of view? What is FOV? So FOV, short form for field of view. Very straightforward, the field of area you're viewing at a time. So really it's just the area that you are looking at one moment. So for example, on the right, you can see a large FOV picture. You're seeing the mountain, you're seeing the sky, the tree, and the flowers. If for a smaller FOV setting, you're not looking at all those. You're only looking at the flower at the time. So you're looking at a smaller area in this case. So what happens in CT is there's typically two types of CT system. I think there's only these two types that I know of. The first one is a cone beam system. So this is how your sample is going to be sitting inside a chamber, how it works. You have an X-ray source, it emits X-ray as a cone, so it spreads out. And you put your sample at the center or in between your source and your detector that your X-ray will pass through. And then you collect the projection. So when you move your sample closer to your detector, you can see you have a larger FOV. But you also notice you don't really have a lot of magnification happening in this case. So if you do a scan, you'll still have a very informative 3D data, but the size of the magnification is similar to you're actually looking at it with your bare eyes. Now, so if you move it the other way, if you move it closer to your X-ray source, you'll see that you have a lot more magnification. You can see via the projection that I show on the right. But at the same time, you have a more limited field of view. You're not scanning your whole sample anymore. There are part of your sample that's not within the field of view, but you do have a high magnification. So this is where the FOV and resolution balance coming from. So to bring out an example that I talk about to give you more idea, what is the situation I'm facing when I was scanning the respirator? So when I was scanning the whole respirator, this is roughly where I put my sample. So you can see there's a picture. How I mount the sample just on the pillar. It's quite close to the detector. So in this case, I was using a FOV setting of about 220 millimeter, and with the voxel size resolution 78.57 micron. When I was scanning the filter can, I scan it here. So you can see it's a lot closer to our X-ray source. But in this case, with a more limited FOV, I do have a high resolution. The voxel size now goes down to 14.29. So this is the balance you have to think about when you're thinking about which FOV to choose and what kind of resolution you want. Now, there's another system I mentioned. Okay, there's two types, right? So what's the other type? Is the other type exempt from this kind of balance you have to do? Well, the other type is parallel beam system. To begin with, you already will have more limited FOV because to focus, you don't have that cone that's larger for you to put your sample. So in this case, you can see the gum tree seed as an example. Already, I'm not really scanning the whole of it, right? With this type of system, no matter where you move your sample, it's the same. You're limited already by the beam size. In this kind of system, you have a fixed FOV because you're not really changing it, and fixed magnification. And there's an asterisk because there are ways to kind of change that, but only change it to the smaller end. So you can change your optical lens to have high magnification, but your FOV will be certainly reduced. So I actually did use this for the example of the respirator for the particles. So for the particle, I scanned it in a parallel beam system, and this is how it looks like. So you can see here, that's the lens I talk about. So my sample is just mounted on a tiny pillar. But I do have a high resolution. So in this case, I do have a FOV quite limited to 10 millimeter, but the voxel size is 1.6 micron. Now, this is a lens I use. I was using a 5x lens. So today, if you change it to a 20x lens, to focus the beam path more, now you actually have a narrower area to image your sample. So if I use a 20x lens, I will have a high resolution, but my FOV still is going to be reduced. So that's the kind of balance you have to think about when you're thinking, okay, what kind of sample size I'm willing to go to and what kind of resolution do I really need? Now, so after this, you'll be like, okay, so how do I choose exactly? So let me plot it for you so you have a more intuitive view. This x-axis is the resolution and the y-axis is the sample size. So when I was scanning the respirator, the whole thing, it's roughly here where it sits in terms of sample size and resolution I use. This is for the valve area I was scanning, and this is for the filter can layers I was looking at. And at the other end, at the tinier end, is the particle I was scanning. So I have the high resolution, but more limited sample size. So the system I chose to use based on the system I have, so Rigaku here, we make several types of X-ray CT system. So for our CT Lab HX, is a benchtop system, actually covers all of them. Only the first one, the whole respirator, is a little bit, maybe it's a bit too large. So that's why I actually scan all of these in our larger system, the CT Lab HV. Covers a lot more sample size range and then similar resolution range, a little bit better at the tail end. And for the particle I was scanning, I use an 3DX, the parallel beam system, where it occupies around this area. So I kind of also just remind you, okay, what those samples are and kind of where they sit. So after this, you might be like, okay, Ted, now I know how to choose a CT. Sample size, resolution, done. But hold on, there's another thing, right? Remember, the sample composition also matters because what your sample is made out of matters. Why? It's because X-ray is an absorption technique. Actually, CT it is. Everything absorbs X-rays, even air, even just air particles, maybe just a little. So everything absorbs X-rays. So what happens is when you turn on the X-ray, it got absorbed by your sample. Before it got absorbed, it has the intensity. After it passes through your sample, you have a measured intensity. And of course, there's an equation to describe the relation, but you only need to know what's important. So T, thickness will affect it. Makes sense. The thicker sample is more absorbed. The mu term is what's related to what your sample is made out of, and also the energy you use. So that's an equation that looks kind of daunting, but you only have to remember it has something to do with your density, your atomic number, and the X-ray energy you use. And because of this, we have contrast. So when you use the same X-ray energy to penetrate through different density and Z material, you can see from the heavier to the lighter one, you'll then have the contrast. That's how you get the X-ray images. So for an example, like a bee here, you can see the details. You can see where the wing is. You can see where the body parts and everything. Now, if you use the same X-ray energy to try to penetrate through very hard to penetrate samples, the contrast will be very little because for the X-ray, all of them are very hard to penetrate, so they might as well look the same. Same can happen if you use too strong of an X-ray for too light of a sample, because for those X-rays, those samples might as well just be air. So for that kind of X-ray setting, you also cannot have a very good contrast. So to show you an image of what it actually looks like, an actual sample, you can see on the left, the same sample. If I'm using a not so optimal setting, I have very low contrast. On the right is a high contrast image. So in this case, what caused these? So we know it's density, atomic number, and X-ray energy. So to get a high contrast, you can't really change the density of your sample, right? Because that's your product, that's your research. If you change it, that's no longer your thing. Same goes for atomic number. So the only thing you can change is X-ray energy. And that energy is tied to your CT system, specifically the type of X-ray source it has. So back to the example I talked about, what about these kind of distribution when I was doing the scans of the respirator? So the same plot, but I changed the left y-axis to X-ray energy. This is where the respirator scan I did. Remember I talked about, I used about 200 kilovolts to scan it, and then the resolution size sits there. This is where the valve scan was done for the filter can layers, and then for the individual particles. And it goes back, let's talk about the cover of energy range for different X-ray CT systems we have. For the HX, in this case, you can see, actually, in this case, because of the energy I chose, I was using 200 kilovolts, the HX only goes up to 130, but still it covers a lot of the range and a lot of the area. But in this case, I did use the HV. It covers a lot more energy range and resolution. And for the now 3DX, I did that for the particle. So just to show you again what it looks like for the samples I scanned, to a reminder of what those are. So these two, the sample composition and FOV versus resolution, really is the key or the core when you ask yourself, okay, which CT system to choose. And with those comes with the question of, what is your preferred sample size? Because there are times now you know the balance between resolution and sample size. Maybe you can actually do some modification to disassemble or cut a little bit so that you have higher resolution. Or it can be the other case. Maybe, you absolutely don't want to cut your sample. Then it's challenging to have a higher resolution. So what kind of feature size do you expect that you need? And also, these two, just a reminder, these two are balancing with each other. So this is one of the key things you need to know about. And then, what is your sample composition? The fact what kind of energy you need to do the imaging. And obviously, other factors like available space, some equipments are larger than the others, and also the budget that you have, you think about to invest in getting a CT system. Now, after that, I would like to actually ask you some questions to have some feedback. So let's head in our second polling question, and I'll hand it over to Angela.
Thanks, Ted. So I have launched the second poll question, and the question is, what matters the most for your application? Is it sample size? Is it resolution? Or maybe X-ray energy is most important, or maybe something else completely. So there's an others category. So everyone is coming in. We've got about 28% of responders. Almost half of you have responded. We'll give a few more seconds, but Ted, we have kind of a clear leader that's coming out here. So I'm going to give a few more seconds, 3, 2, 1. I'm going to end the poll. I'm going to share the results. It looks like 31% it's sample size, 62% resolution, and 8% X-ray energy, and 0 for others. It's interesting. So resolution. So I'll stop sharing and send it back to you, Ted.
Okay. Thank you, Angela. And also, again, thanks everyone so much for answering the poll question. It tells a lot. And kind of what I expected, it makes sense because resolution, whether you can see or cannot see what you're trying to see, right? It's very important. You have to be able to see it. And then the sample size, because if you want to use CT, chances are you're also very keen on keeping it a non-destructive technique. So if you have to cut your sample open, then sometimes you feel like, okay, there's more things I need to consider about if this is worth it to do. So that's kind of what I expected. And X-ray energy, I can imagine maybe for the people who answer X-ray energy, you already have some experience with X-rays before. Maybe you did some scans before and like, it's not turning out too well. What am I doing wrong? Why is it not showing up as I'd imagine? So that it actually leads into what I'm going to talk about next chapter really well, which is after knowing how to select your X-ray CT system, which system to choose, what are some of the things you need to take notice of for both in general using CT or when you're mostly dealing with smaller scale, high resolution, or the other end, maybe larger samples or more high density samples and so on. So let's talk about some practical strategies. So it's not going to be super in-depth into all the sample mounting and everything because I can probably make another webinar just based on that. But I think it's still going to be very informative. So practical strategies for Multiscale CT. Sample preparation. Sample preparation is one of the key things because of it's a two-side of the things. You're having a very versatile technique here. So you can put a lot of different things in there. So that means you don't have a very standardized sample preparation process. It's not like you always have to polish it and put it in this mount with this size. No, it can be all sorts of different size, right? So what are the things you need to know about when you're doing sample preparation? Sample size estimation. What exactly is the sample size I'm using? Or is my sample big or small? Secondly, try to push for that FOV and resolution balance limit because now we know, okay, I'm trying to balance between imaging a larger area and also having high resolution for my sample. There's some ways or some techniques I can take to maximize that so I can still get the bigger area, but also high resolution. And then we'll talk about some more scale-specific challenges. Like if I'm mostly focusing on lighter, small materials, what are the things I'll face most often? It's specifically some of the challenges you will face more often than people who are not focusing on smaller and lighter materials. And also on the other side of the spectrum, while the larger, heavier samples challenges you're going to face when you mostly scan samples like that. So first for sample preparation, sample size, what exactly do we mean? Like when we're talking about CT sample size, is it volume or is it the height, the width? So for CT to work, you have to put your sample in the chamber for it to rotate. So in this case, you see you have an X-ray source, and let's say we put a mannequin there, a small, tiny mannequin. Now to scan it, what is the sample size I'm asking myself when I scan this type of sample? So let's also have a top-down view so we have more idea of what, how big of a space this sample is occupying. So when I talk about sample size, because the sample has to rotate, I'm talking about the actual area or the volume that the rotation will take up. So when we talk about how big your sample is or the sample size estimation, we're mainly talking about this diameter of the cylinder area that is taking up. And it can change easily just by how you mount your sample. Let's say today it's the same mannequin, but you just put its arms up, so like this, and this is a top-down view. The same sample, if you scan it like that, it's taking up a larger space. So now you have a larger diameter for your rotational cylinder that's taking up. And you can also just mount it a lot different ways. In this case, maybe just tilt it, and then you'll take up an even larger area. So this is the sample size we talk about when we're mounting our samples. And this actually will give you a lot of ideas to think about how you want to mount your sample, because a lot of times the samples are not a regular shape. And just based on how you can mount your sample, you actually decide how close you can get to your source and how high of a resolution you can achieve. Now, talking about pushing for resolution limit. So we talk about the FOV and resolution balance here. Let's say I want to again scan this mannequin. With this FOV, I have the full mannequin in the field of view. I can scan the whole thing in one go. But I kind of want high resolution, right? If I do that by putting our sample in front of the source, closer to the source, now I got this. Like, okay, this is a good resolution I want, but I don't have the full sample. So do I have to compromise? I cannot just scan it with that kind of resolution. Actually, you can do something like this. So if you position your sample first, maybe just scan the top portion, and then do another scan at the torso area, and then another scan for the legs area. You can stitch them all together. You can do a stitch scan to stitch multiple parts together, so you still get the full sample, but now with a higher resolution. So you have a lot more ways to work your sample vertically, z-axis, what we talk about. And it's not limited just to one larger sample. You can also do this with multiple samples. Like, okay, I want to scan a lot more samples in a same setting. You can actually stack your sample together and then do these kind of scan, and then you'll have the scan of all those samples, but with higher resolution, compared to if you align it other way and then try to accommodate the whole volume for them to all rotate in that whole volume. Now, let's talk about some scale-specific challenges that you'll face more often. Start with the smaller, lighter samples. So here we have an example of, it's like a fiber or a hair or like some grass tips with a 3D render at the center you can see. This is actually one of the scans done by my colleague Aya, and she did a webinar talking about these before. So I'm reusing some of the very informative pictures. So when you scan it, and then you imagine you cut it open virtually and look at the cross-sectional views of these fibers. What do you expect to see? Something like this, right? The cross-sectional views, the cylinders, the circles of these fibers. Now, maybe actually when you do the scan and you come back, instead of seeing these circles, you actually see something like this. Like, there are some distortions happening. Is it because my fibers are jagged? It's not a smooth surface. Specifically, let's look at one of those, at the more distorted one. So to put them side by side, on the left is what it's supposed to look like. On the right is the non-ideal version of the scan. So what happened here? For the left picture, it's from the sample scan that is very still, that your sample is not moving. On the right, what happened was during the scan, your sample moved. So technically, you can say this is not just limited to smaller samples, but these movements are very tiny a lot of times, and it only shows up and you'll vividly notice it when you are also pushing for that resolution limit. Maybe they only move for a couple microns or tens of microns. When you're scanning it at a larger field of view with low resolution, those kind of micrometers, twisting or shaking doesn't matter. But now when you're scanning very high resolution, they do. So sample mounting and sample stability becomes very important. And actually, this is something I faced during my PhD research. I was scanning something very tiny. And for the longest time, I just couldn't get a very good scan because it's somehow just blurry. It's always blurry. Why is it blurry? Because it's always moving a little tiny bit. So I spent all the time just to make sure, okay, I need to find a way to stabilize my samples. But when I was scanning larger samples because I was also doing kind of multi-scale studies. Larger samples, I didn't have this issues. I only encountered and noticed it as an issue when I was scanning smaller stuff. Now, on the other end of the spectrum today, if you're scanning larger samples, technically also not just for larger sample, but for heavier samples in general, the samples that absorb your X-ray more aggressively, the higher attenuation sample, so to speak. So in this example, this is not really large. It's like just a palm size, but it is a very heavy sample. So similar to large sample, it will absorb a lot of your X-rays. So look what happened when I do a scan without any consideration and no adjustment. The scan actually looks kind of horrible. It looks kind of nasty, like, oh, a lot of things are going on. You have these weird lines, weird dark lines in between your structures. So what is this? So these dark lines are caused by, for example, today when you're scanning your sample, so to highlight what I'm mentioning about, you have a very high absorption sample. So when you scan it from one direction, your X-ray travel like this, right? But if other parts of the sample gets in the way, like for example here, a lot of the X-ray are already gone before reaching the larger part of this scan I was mentioning about. So you have kind of like a shadowed area that's just having less information that's reaching your detector. Now you turn your sample 360 degrees and scan it from another direction, see what happens. Now, from another angle, you also have a blockage of signals. So it ended up creating all these kind of blind spots that you cannot really see very well. So this is called metal artifact, but technically not limited to metals. As long as your sample is very absorbent of X-rays, it can happen. It just happens most often for metals because they are inherently high Z materials compared to a lot of other elements on the periodic table. Now we have also other stuff, like here, there's a light glow on the top of this portion that actually doesn't exist. It's another artifact or a distortion caused by something called a beam hardening. So I'm not going to delve too deep into this. In fact, these are topics of its own, specifically talk about high attenuation things and what you can do to fix it. Actually, in fact, already did. We did a webinar last year specifically talking about high attenuation samples. If you're interested in it, you're welcome to check out the recordings. But just kind of like a sneak peek to show you there are things you can do to fix it. In this case, just that it's beam hardening. After applying all the things you can do to correct for these kind of heavier sample problems, you can actually get a scan like this for the same sample. Yeah, so those are the scale-specific challenges and also the sample mounting techniques and things that you need to think about when you're doing multiscale structure analysis with CT. So now let's head in our last portion of the day, examples of multiscale CT studies. The respirator is already quite an intuitive demonstration of how you can do multiscale structure analysis, but I would like to include some more other examples of different study and different fields so that to show you what people can do and people are already doing in all these different fields. First is additive manufacturing. You can see on the left, this is a laser melted or the electron beam melted metal powder alloy tab. So on the right is a 2D cross-section view. So I can actually show you as if you're slicing it throughout the sample virtually. We actually didn't cut the sample, we just scan it so we can see this internal view. And you can see a lot of area having gaps, having pores, or even not properly molten particles that's still trapped in there. So for additive manufacturing, a lot of times it's the powder quality that's contributing to this kind of defects. So you might want to study, okay, let's look at the powder with a high resolution to see what happens. What's the quality of my powder? So in this case, I show a scan here. This is a scan of the same powder, exactly the powder we used to make the sample that you saw earlier. And in this case, to show some analysis like porosity analysis. And this is a very big topic for additive manufacturing, powder quality and powder porosity, because porosity, you cannot see until you cut it open, right? So conventional technique, you have to do 2D sectioning, SEMs, and this is very popular in additive manufacturing because CT just show you in 3D and you just scan it. And this is one example. And you can always ask other questions like the morphology, size distribution of the powder. They're also very important in terms of how they behave in the melt pool when you're doing the printing. So, in fact, we actually collaborated with Geodic in here. This is where we get our renderings to make a AM solution guide using CT, and it's already published. So you're welcome to go check it out. I think Caitlin will share the link in there in the chat. Next, this is example of battery. So there's another example that okay, you don't want to cut it open if you don't have to for multiple reasons. So in this case, we did a whole scan of the battery to see what's wrong. And in this case, specifically the delamination of the cathode anode. And then the high resolution scan at the center delamination area. And on the right, there's a 3D render of the data sets. You can see the whole battery, and then later we do a high resolution scan. In this case, we didn't cut the sample open. It's the same exact battery. We just move it closer. Now you know how it works, FOV versus resolution. We move it closer to our X-ray source, and we'll do a high resolution scan of the area we're interested in. And I did the segmentation of the cathode and anode. So if you're interested in the packing density and all other kind of studies, this is how you can do the analysis. But in this case, we're specifically looking at the delamination. So I did a thickness estimation of these delaminated area, the porosities in them, to showcase in 3D, and also spatial data to show you where they are. And the next example I'm going to show you is in life science. So life sciences also, we have a collaboration with the Sam Houston State University. On the left, the whole scan of the lizard. So they can already look at the whole lizard to notice if there's anything of interest, like the length of some of the arm bones. And we know for a fact for many different species, the skull area is actually what makes them different. So we did high resolution scan on the same lizard you see on the right, but with high resolution, you can see, even count the teeth and look at the shape of the teeth. Those are the kind of feature of interest they are interested in to do the study, to basically separate different species and quantify what's the difference in different lizard they collected from different areas. And the last example for today is a CFRP carbon fiber reinforced polymer. So on the left, it's a scan courtesy to Old Dominion University. I did the scan for them on their samples. You can see here, there's a bunch of different slabs of these carbon fibers glued together using polymers. And if you're interested in how they overlap with each other, this is how you can do it with CT with the 3D data. And if you're interested in more intricate details, like, okay, how the fibers and the polymers are bonding together, what's the crack situation between them, what's the debonding situation, you can also do that with CT with now a high resolution scan. Now you have multiple scales, a larger scale with different slabs, or smaller scale individual fibers and the fiber conditions with the polymer. And with that, I've shown all the examples I want to share with you. And hopefully with today's webinar, you learned what multi-scale structure analysis is. Why is it important, not just for research or manufacturing, and also how CT can help you in both cases. And for choosing CT system, what are the limitations and requirements you have to know about when deciding how CT can help you for your need, and also some of the practical strategies for different scale that you're looking at. And finally, some different examples from different research topics and field doing multi-scale studies using CT. And with that, we'll do our final Q&A session.
Thank you, Ted. We got a few questions that came in. First question is, how did you measure the particle sizes and how did you separate them? I believe this is in relation to the respirator cartridge, closer to the presentation.
Okay. Yeah, so that's a good question. So for CT, it's kind of, analogy-wise, it's kind of like any imaging technique. You see the particles, either in SEM, OM, CT, you see it, but how do you separate them? You have to define what they are. So what we do here is a technique called segmentation. Basically select individual voxels that's representing these particles inside the whole data sets. And once these particles are labeled, meaning you're telling the software, hey, these are the voxel sets of this particle. And then you can ask question, okay, how many number of voxels are there? And you know the size of these voxels, and then you can tell the volume, for example. And to separate them, sometimes, yes, when you have two particles that's super close to each other, it might be hard to directly just separate them. And there are some techniques, analysis technique to kind of separate them, something called watershed segmentation. You can probably look it up. In this case, I used Dragonfly. They actually, in fact, Dragonfly 3D World, they do have some tutorial videos to actually teach you about watershed segmentation. So you can check those out.
Thank you. Our next question is, what are the benefits of CT if the feature that I'm interested in still requires me to cut the samples?
Mm-hmm. Yeah, that's a very, very good question, right? And I can see that's the one that when you learn that, oh, there are some cases that still have to do sample preparation, then why should I use it, right? How does it differ from other destructive techniques? So first of all, the destruction is actually quite limited because it's not like you have to polish, you have to make it flat, you have to do all those things. The only thing you need to do any preparation is just that it can fit. It can fit into the equipment, it can fit the kind of resolution you want to use. Second of all, CT is an inherently 3D data provider. So you're not just looking at 2D cross-sectional views, you have the whole comprehensive 3D clone of your data, of your sample. And a lot of times, this is very crucial and very informative to correlate with conventional destructive techniques. In fact, I also did that with my research. I also did SEM. I also did nano-indentations. I also did EDS to composition, spectroscopy, all those kind of things. But they all converge back to CT because, hey, I just had the whole thing at the palm of my hand, a 3D structure. Now I can correlate those data back. So even if in those cases you don't just get what you want by scanning CT, and you do still have to do some form of destructive technique, I feel like the information density is still very, very helpful, and you still get a lot out of CT.
Thank you. It looks like we have time for one more. How did you align the high resolution to low resolution data set for the battery example?
Okay. So that's also a good question. I actually just talked about this with someone in our company not too long ago when we were chatting about this. So a couple of ways you can already know, okay, I want to do this correlation. So you just scan it as is. You don't even touch your sample. You just scan it at a higher FOV, smaller FOV, and then you put it in the data loader because you didn't change any dimensions. As long as you just put in the right size, it'll already be quite aligned. But what if today you do it separately? Because again, this is a visual technique. So you see exactly what you see. So if you see the layers, you see the features, you can actually virtually overlap them in the software. So you can see them together. And what I do is you make one of them kind of semi-transparent, and then you really just drag the data together and then align them. And you can see the features and match the voxels. And even, I think, again, in Dragonfly, they actually also have some software to help you with that. But using these 3D, actually visually, you can see them align. That can help you align two data sets together. And that does tell you that if today your data is looking very, very samey everywhere, yes, then you will have some challenge trying to align them. If everywhere looks the same, how do I know which part is it? It is something that's quite challenging when you're trying to align the data that doesn't have any features that you can use as a kind of like a reference.
Okay. Thank you for that. Well, looks like that is all that we have time for today. Any unanswered questions, we'll follow up with you after the webinar. And then if you want to watch the recording or share with your colleagues, the recording will be available tomorrow. And if you would like to sign up for our X-Ray CT newsletter, we have webinars, workshops, and blog articles, as well as application notes available there. And I will drop the link for you to subscribe. And we look forward to seeing you all at the next webinar. Have a good rest of your day.
Thank you for coming. Thank you.
Hi, everyone.